Okay, subspaces. So this is a very general mathematical idea. As soon as you have any mathematical object, like abstract object, like a field, a ring, group, if you know what a group is, whatever, then you will always have sub-field, sub-ring, subgroup, sub-vector space, vector subspace in this case. So what is that? It is a subset of your vector space. So you have started with a vector space V, and then you have a subset, certain vectors inside it, which also form a vector space. So let me define it. So definition. So let V be a vector space over F. Soon enough I will stop even writing this over F, because we always work over some field, and usually I will denote it by F. So when you have a general definition, you don't care which field it is. But for now, let me just say, let V be a vector space over F. Okay, so a subset, say W, inside V is called a subset, a subspace of V if the following properties hold. So let me kind of explain the idea. So the idea is as follows. So if you have a subset of a vector space, you want it to be also a vector space, to be a subspace, but also you want it to be a vector space with absolutely the same operations as in V. So of course it will be really strange if you have vectors in V, but you add them in a different way than you add them in W. Of course, you can do such thing, but it will be not a nice object to work with. So basically, what we will write now are a bunch of axioms, a bunch of properties, making W a vector space on its own with the same operations. So here is the first one. For every two vectors W1, W2 inside V, inside W, W1 plus W2 is also inside W. So usually people say also that W is closed under addition, meaning when you sum up two elements there, you still get an element there, because a priori you can get an element in V. So second one is that for every lambda in V, lambda times for every lambda in F and W in big W, lambda times W is also inside big W. So when you rescale a vector in big W, you also get a vector in big W. That's a property. So just two simple things to check. Sum of two vectors is there, multiplication on a scalar is there. So so that's a definition, and we will come to examples very soon, but the reason why this definition makes sense is because of this simple proposition. So if W is a subspace of V, then so firstly, zero vector is inside W. So zero vector inside V is inside W. Second, for any vector V inside W, minus V is also inside W. So additive inverse is also inside W for any vector W inside W, W inside big W. And three, the main important part is that W is a vector space with same addition, multiplication on a scalar, inverse 0 as V. Just it is a vector space, and all important things, how you add, how you multiply on a number, how you find inverse, what is 0, everything is just the same as in V. So that's the statement, and proof is basically obvious. So let me just very quickly, so why 0 is inside W? Just because, you know, by property 2, 0 is inside F, and 0 times W is 0. So this is inside W by property 2, and so this is inside W by property 2, and this is how we prove 1, and 2 is, so this is proof of 1, proof of 2 is minus W, as we already discussed, is minus 1 times W, which is inside F, which is inside big W. So this is inside W as well, and this is because of this 2. Sorry, we confuse. Let me denote it 1, 2, 3, and then it is 1, 2, and this is by 2, just press bracket. Okay, and 3 just follows from the above. Basically, just, you know, think a little bit about that. Okay, we have W, we know how to add things because this is how we do it in V, and because of property 1, this definition is well defined. You can define this map from W times W to W, which is addition, which is just add them as in V. And similarly, F times W to W, such map exists because of property 2. And then all the axioms just follow from these observations and from here. Notice that things like, for instance, why addition is associative, this universal laws, like for every element in V something happens, will be definitely true in W, just because, you know, they are true in any vector in V, and W is a subset, that's why. So checking axioms like 1a, 1b is commutativity, right? No, 1b is 0, 1c is commutativity, properties 3, which are distributivity, all of that is immediate just because they are true for every element in F, every element in V, so for every element in W as well, because W is inside V. Okay, so this is a definition of a vector subspace, and it's actually a vector space on its own, and this gives us tons of new examples. So let me now show you more examples of vector spaces and subspaces inside. Okay, now I want to give some examples of subspaces. So some examples of subspaces. So let's start with the following very important example. So example 1. So let's take as a vector space R3, and you can think of it as just usual three-dimensional space, you know, with coordinate system. And points, vectors here, are just points, you know, considered sort of points x, y, z, where x, y, and z are in R. So what can be a subspace? So for instance, I can consider a set of vectors W consisting of such points whose coordinates satisfy an equation. So x, y, z such that 2x plus 3y minus z equal to 0. And that's an example of a plane. So it's a plane. So why it is a vector subspace? Let me check that. That's really simple, but just for now. So if vector W is inside the space W, having coordinates x, y, z, then for every lambda real number, so we know that 2x plus 3y minus z is equal to 0, and then for every lambda we can just multiply it on lambda and see that 2 lambda x plus 3 lambda y minus lambda z equals to 0. So it means that lambda times x, y, z is inside W. And similarly, if we know that x1, y1, z1 and x2, y2, z2 satisfy W, are inside W, then we know that simultaneously they both satisfy the same linear equations. 2x1 plus 3y1 minus z1 equal to 0, 2x2 plus 3y2 minus z2 equal to 0. And then we can just add them up and we get the 2x1 plus x2 plus 3y1 plus y2 minus z1 plus z2 equal to 0, which implies that if this was w1, this is w2, this is big W, then w1 plus w2 is inside w. So that's an example of a computation like that. So basically, this is a vector space because this equation is homogeneous. When you have one solution and another, you add them, you get again a solution of this equation. So remember now lecture from the first lecture. So linear algebra is about linear phenomena. Homogeneous systems of equations give you this linear kind of objects, and this is an example. Their solutions form a subspace of V, and this is very general idea. Okay, so maybe more generally, just a generalization. So we can take V being equal to Fn, and now this is this coordinate vector space, and this consists of the sequences x1 and so on xn, where this xi are in F. And then, so for a1 and so on an in F, consider W being a set of x1 and so on xn, such that sum ai xi equal to 0. So sum from 1 to n, ai xi equal to 0. So basically expanding it a little bit, so a1 x1 plus and so on plus an xn equal to 0. So this W is a vector subspace, absolutely the same proof. Rescale, add to such solutions, you get 0. So W is a subspace of Fn. So later on we will see that it is very closely related to Fn minus 1. It will be called a hyperplane, but we will talk about it later. So that's a very classical, important example. Okay, example number 3. So let V be f of x, polynomials. And then if d is some integer number, maybe 0, then we can look at W will be a set of polynomials of degree less or equals than d. So that's a trouble. I have no idea how to define it. Maybe a notation will be something like fx in brackets less or equals than d, or something like that. I honestly don't know a good notation. So that's a vector subspace of space of polynomials. So why is that? That's because, that's because of some properties of degrees. When you have two polynomials of degree less or equals than d, when you add them up, degree is less or equals than maximal of 2 degrees, so in particular truly less or equals than d. When you multiply a polynomial on a number, then its degree either does not change if the number is non-zero, or if it is 0, you get 0 and it has degree minus infinity or whatever, so it's definitely less or equals than d, and that proves that W is a vector space. So remember in the beginning of the lecture about polynomials, we thought about polynomials as these strings of numbers, infinite strings, but with zeros starting from some point. And if you have f of x less or equals than d, it means that these are actually strings of numbers where you have something, 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 and then 0, 0, 0, 0 in every position greater or equals than d. So as soon as you have a term greater or equals, than d plus 1, you'll have zeros. And so basically you can think of such polynomials as strings of numbers in f. And so this vector space is not particularly different from f power d plus 1. That's another example of this isomorphism idea we will talk about later on. Perfect. So this is the third example of a subspace. Set of polynomials of degree less or equal than d is a vector subspace. Okay, what else? So vector spaces, their subspaces have a bunch of interesting properties. Let's talk about something. Okay, so subspaces have some properties. Let's talk about something. So let's define what is intersection of two subspaces. So definition. Okay, so here is a little hard notation. So let V be a vector space over F, and then suppose that we are given a collection, which just means a set of subspaces V sub alpha for alpha in I, where I is some set of indices. So that's confusing. So you have a vector space and you have a bunch of subspaces, and if I have just two or finite numbers, that's simple. I just denote them v1, v2, v3. But suppose I have infinitely many, like, you know, all planes in R3 passing through a fixed point or something like that. Then I want to be able to talk about infinitely many subspaces, and I label them V alpha, where alpha is inside some set of indices, which can be anything. For instance, you can think of, you know, just I consisting of two numbers 1 and 2, and then you have v1, v2 inside v, just a pair of subspaces. Then their intersection of course is usually the set of vectors v inside v, such that for every index alpha in I, v is inside v alpha. Usual set theoretic intersection, as in set theory. So, I don't know why it gives this definition. That's actually just a definition of intersection of sets, nothing else. And then a little proposition is that intersection of v alpha, alpha in I, is a subset of V. So intersection of a bunch of subsets is a subspace of V. So proof is trivial. I mean, we need to check property 1, property 2. So let's prove that this is a subspace. So suppose v1 and v2 lie inside, let me denote it by w, lie inside w. Then for every alpha in I, v1 lies inside v alpha and v2 lies inside v alpha. We apply property 1 of subspace for each v alpha, but then you can add them up. This is just a definition of W, and then we apply property 1 of a subspace. You can add two vectors in a subspace. Then for every alpha inside I, v1 plus v2 is inside v alpha, but then of course it's inside the intersection. And so this is part 1 of the definition of a subspace, and 2 is of course similar. Okay, why talk about that? Because that's a very important example of a subspace. So for instance, let's consider For instance, let's consider R3 as before, and then let V1 be space xyz such that 2x plus 3y minus z equal to 0, some plane, and V2 is another plane, xyz such that 3x minus z equal to 0. And then V1 intersect V2 is a line passing through 0, which is intersection of two planes, you know, something like that. And that's again as subspace. So a line passing through the origin is a vector subspace of R3. That's an important example. So what else I want to tell you about vector spaces? Okay, maybe that's fine about that. I want to tell you a little bit about what is this notion of isomorphism, which we will talk about in detail next week. Okay, let's talk a little bit about isomorphism. And this is just the idea. I'm not going to work out all details here, we will do it later on. So, when you have two objects in mathematics, it's very important to understand when you think of them as being the same. So that starts as early as you encounter what is a number, what is number 5. So suppose you have a set of, 5 cats, 1, 2, 3, 4, 5. That's a lot of cats. And suppose you have a set of 5 something else, whatever that might be. Let's say 5, 5, 5, 5. 5 crocodiles. 1, 2, 5. Okay, so we know that both sets represent a concept of a number 5. Why? Because, their number is the same, and when you think about number 5, you think simultaneously about all sort of sets containing exactly 5 elements. And here we have a key fact that we say that these two sets have the same number of elements if there is a way to identify elements in the first set with elements in the second set in a one-to-one bijective way. So basically, numbers are classes of equivalence of finite sets modular an equivalence relation, which is there exists a bijection between two sets. Notice that this bijection is not unique. There are lots of different ways to say how these 5 crocodiles have the same number of elements as these 5 cats. You can relabel crocodiles in some way, and then you will have another bijection. So basically, 5 equal to 5 in lots of different ways. So that's a little philosophical remark here. And we will talk later on about this idea in lots of details when we talk about permutations, because permutations are exactly ways in which 5 equals to 5. But now we come to vector spaces. So, of course, if I introduce this notion of a vector space, it makes sense to ask when two vector spaces are the same. And naive definition is two vector spaces are equal to each other if the sets are equal, fields are equal, and all operations work in the same way. And this is okay, except that sometimes, it can happen that you see two vector spaces, which if you relabel objects in the first one and relabel scalars maybe, there is a way to identify them with another vector space, and everything will work out. All operations will work the same. And maybe there are tons of ways to do that, but if at least one exists, we call two vector spaces isomorphic. So isomorphic vector spaces are vector spaces where there are two vector spaces, and between them there is a map, which is a bijection, so it is like that, and it behaves nicely with respect to addition and multiplication on a scalar in a sense that if you do the separation here, the result will be also the result of the separation in the other space. And then basically you can think of this isomorphism as a way to relabel objects in V1 to get exactly objects in V2 so that all operations will work consistently. So this is an idea of isomorphism. So let me write down the definition now. So two vector spaces over F. It's very important that they are over the same field. V1 and V2 are called isomorphic if there exists a map phi from V1 to V2. So sending vectors in V1 to vectors in V2 such that firstly, phi is a bijection. So I remind you, it means every element in V2 comes from some elements in V1, different elements in V1 go to different elements in V2. It is equivalent to the fact that there is a map in other direction, which if you go one way and backwards, you have identity map, and similarly here. And the second property is that for every two vectors V1, V2 in the first vector space, if you take phi of their sum, it is the same as first take phi and then add them up. So addition in V1 and V2 work consistently with respect to this relabeling map. And another property is that for every lambda in maybe 3 in F, phi of lambda F, lambda V equals lambda phi of V. So if you rescale one vector and then send it somewhere, your vector is rescaled. So this is a definition of an isomorphism, and when such map exists, vector spaces are called isomorphic. So why this is important? Because we have seen in this lecture already quite a lot of examples of isomorphic vector spaces, and intuitively these were vector spaces which looked kind of the same. And again, I leave details to the next week, but let me just give you a few examples. So example 1, probably the one you know from high school, is that this vector space of oriented segments is isomorphic to R2 being this coordinate vector space. And what this map does, you take a vector AB between points x1, y1 and x2, y2, and you associate to them, so you want just one element in R2, so you take x2 minus x1, y2 minus y1. So that's what you do. And then you check that when you rescale it here, it's the same as multiplying on a number here. When you add here, it's the same as add coordinates here. And that's exactly what our isomorphism property requires. And the second example will be that if you take vector space polynomials f of x of degree less or equal than d than d, that's isomorphic too, and this is a notation for isomorphic. Sorry, so this is this isomorphic is denoted v1, and then 2, like equality with this beautiful arrow, v2 is isomorphic to f power d plus 1. And you just take a polynomial of degree d, each of them is a0 plus a1x plus adx power d, and then you send it to a vector a0, a1, up to a d. Perfect. So then when you add them and multiply by a number, it happens exactly in the same way with these sequences as with polynomials. And also it's a bijection. So every polynomial is completely determined by its coefficients. So that's another example of isomorphism. So basically when you see two vector spaces which sort of looks similarly to you, probably that's because they are isomorphic. Okay, finally, so this is the end of this first long and hopefully fun lecture. I want to give you an amazing example of a finite dimension of a vector space, which is really beautiful example. Okay, final example of vector space. So that's really interesting one. So an interesting example of a vector space. So, okay, so here is an interesting example. So firstly, I need to specify a field, and field will be just F2. So field with two elements, it has two elements, I remind you, 0 and 1. And I won't even put brackets here, just 0 and 1, and you remember 1 plus 1 is 0, and so on. So then I need V. So V will be subsets of a set 1, 2, 3, and so on n, which I will denote just by n in brackets, with n elements. That's cool. So my vectors are subsets, and my field is filled with two elements. Okay, so now I need to define addition. So what will be V times V to V map? So I have a subset A and a subset B, and these are two subsets of the same set N. So then the operation will be a new subset of the same set, and this subset is denoted by a triangle B. It is called symmetric difference. So it is union of A and B minus intersection of A and B. So let me draw a picture. So this is A, this is B, and then union is everything in the union, and intersection is this one. So I subtract intersection from the union, and I get that. So all elements, so this consists of all elements X inside A union B, such that X is not in A, or X is not in B. So this is my addition. And notice that here, even simplest properties require some check. So also multiplication on a scalar, I have just two numbers. So 0 times A, so now I'm defining this F times V to V map, will be just 0, empty set. That will be just empty set. And 1 times A will be obviously A. And the empty set is actually 0 vector. That just follows because we know that 0 times A should be a 0 vector. Perfect. So then there are tons of things to check. So checking axioms is fun. So why it's fun? Because, for instance, let's check that A symmetric difference with B symmetric difference with C is the same as asymmetric difference with B symmetric difference with C. So this is just axiom 1.a, associativity of addition. Here it's not trivial, it's a property of set theory. So you have A, B, C. So what is A symmetric difference with B? This is that. That's A, B, C. And then symmetric difference with C is you add elements of C and you add this, and then you take away elements which are in intersection of the symmetric difference and C, which is this guys. So you take them away, and so what you end up with are these elements in A which are not anywhere else, elements in B which are not anywhere else, elements in C which are not anywhere else. These three beautiful triangles are not there, and also the intersection of all three. So this is basically the same as this guys plus this guys plus this guys plus intersection of all of them, and elements which are in A and B but not C, and similarly for three other sets, are out. And of course, if you do it in some other orders, it will be the same thing because the construction is sort of symmetric, so you get the answer, which is this addition is associative. And for instance, if you take 2A, which is A symmetric difference with empty set, of course you have A, you have empty set, their intersection is empty, their union is A, so this is just A, and so on and so forth. So you can check all the axioms, and of course it's a little bit routine, but fun, and you get a set. You get a vector space. So of course that looks extremely maybe surprising and confusing. So the question is how one should think about it in a more nice way. So first let's ask how many elements are there. So in this V, the number of elements is just the number of subsets of V, which is 2 power n. Okay, so to understand nicer what are elements of V, so how to think about these sets as vectors, it makes sense to introduce some sort of coordinates. So how to encode a subset of a set. So let's do that now. Okay, here an idea from computer science comes in. So suppose you have this V, these are subsets of this 1, 2, and so on, n set. So how to think about them in a nice way, more kind of algebraically. So a subset V A inside V inside n can be coded by a string of zeros and ones. So you have a string x1 up to xn, where each x1, xi is 0 or 1. Is 0 or 1, where xi is equal to 0 if I is not inside A, and xi equal to 1 if I is inside A. So that's exactly how you can code sets. Let's code it, denoted for instance by S of A, which will be a string corresponding to a set A. So example, for instance, if you have a set 1, 2, 3, 4, and you have a subset, this is your 4 set, and you have a subset 1, 3, 4. So this is just as a string, so this is A, and then S of A is 1, 0, because 2 is not there, 1, 1. So if B is, for instance, 1, 4, then S of B will be similarly 1, 0, 0, 1. Okay, so that's a nice way to think about it, and of course we see that the number of such strings is exactly 2 power n. And how the question is, okay, so what is A symmetric difference with B? So we need to take elements which are in the union. So in the union we have 1, 3, 4, and then subtract intersection 1, 4. So this is just 3. And so S of the symmetric difference is nothing but 0, 0, 1, 0. Okay, how are this vector and this vector and this vector are related? So there should be some nice rule which tells us how to compute the code for symmetric difference of a sets, which is sum of vectors in our fancy vector space notation, of these two guys? And the answer is very simple, just think about it. So you can see that for every coordinate, you just add this guy's modulo 2 in our field F2. So basically what happens here, because 0 is 1 plus 1, 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 1 is 0. So actually this is nothing but S of A plus S of B if we think of this x1, x2, x3, x4 as vector inside F2 power 4. And this is in general true. So what is true is that if you want to consider if S of A equal x1 and so on xn, and S of B equals y1 and so on yn, and these guys are inside F2 power n, so now you not only think of them as just strings of zeros and ones, you think of them as vectors in this vector space, which we discussed before, coordinate vector space, where you add them coordinate twice. Then S of A symmetric difference with B is S of A plus S of B. And this is really trivial because to understand whether an element in the symmetric difference, you need to see whether it is. So if it is, you can just check it coordinate twice. If your element is neither here nor here, then it will be not in the symmetric difference, and that's consistent with the fact that 0 plus 0 is 0. If element is in exactly one of those, one of them is 0, another is 1, then it will be in the symmetric difference. And 0 plus 1 is 1. And if it is in both of them, so you have 1 and 1 here, then it will be not in the symmetric difference because it is in the intersection. And that's consistent with the fact that 1 plus 1 is 0 in F2. Cool. So what we get? So S from V to F2 power n is an isomorphism. So basically, it sends every vector, which is a subset, A, to S of A, and it sends sum to sum, as I just explained, and if you multiply this on 0, you get empty set, and of course S of empty set is just a string of zeros, which is exactly what is 0 vector in F2 power n, and when you rescale, you can multiply by 0 or by 1. If you multiply by 1, nothing changes. If you multiply by 0, you get 0. So you get an isomorphism. And now you see that basically a vector space over field with 2 elements, and this vector space F2 power n has an interpretation. You can think of them as all subsets of a set with n elements, with a wonderful operation being symmetric difference. Okay, that's it. So I hope that you have now a lot of interesting examples of vector spaces, and in the next part of this lecture I will talk about linear dependence and when a bunch of vectors generate a subspace and things like that. Have a great night.